There you go. So we shall be starting, and it's a great pleasure to welcome Professor Valka Sukic. The technology is technology. It's not the first time that we this year, and well, this type of ability on the last. And the well has all of his degrees from the technology. No.
One from Caltech.
But it's all of his degrees from the technology. I said that he got a PhD from Caltech in 2008, but I'm realizing that doesn't come together very well.
But I did return to the exact same department of my undergraduate.
Yes, as a faculty member to the technical department of electrical computer engineering, and it has also had appointments in the industry with Hitachi, if I'm not mistaken, right, and then with Western Digital, as well, spending some time in Lausanne, as a visiting scholar. He received several awards, mostly for work on storage systems, and which is his primary expertise. And please on the seminar, and know that Professor Ryan is also attending, right? Here, but is here with us electronically, and with that we shall start to talk about genomic compression.
I'll first say hi to Prakash. Hi, Prakash.
Hi, Yuval. How are you? I'm sorry I can't be there.
Of course, thanks.
I hope you're well and
It's always fun.
looking forward to your
I'm here.
seminar. One request, I
Like
think
the magnet
you're far away
coding
from
theorists.
the microphone, it sounds
Best
like.
one, but good place to be. So today I will talk about some relatively new work on codes for genomic data. So there will be some details in the talk, but I want to make sure this is like a very leading place, leading institution in information coding theory. So I want to make sure that the big message will not be lost in the details. So I'll start with this executive. Oh, let's see the titles.
Hi, Yuval, can you hear me? Hello?
Yeah, they keep changing the...
Can Adwe or anybody hear me? Hello?
Right on the
Shagnik, are you there?
routing meeting controls.
Okay, great. So I want a big message to carry through, and that is if what we see at the top here is a communication system, coded communication system, where we have a coder and a decoding algorithm, and in between there is something. I intentionally don't call it a channel, not to confuse you, because we'll not talk about channel coding today, but source coding. But what we have in this talk, in this work, is some new guy that is added in between the something and the decoding algorithm, which we call an alignment. For now, it's maybe not clear what it is. But what it does is now the decoder consists of two things. One is the usual decoding algorithm that we all know, and some other entity we call an aligner that is kind of in between the channel and the decoder, and that means that we need to construct code differently. Here we only care about the channel and the decoder. Here we also need, when we design code, we also need to worry about this new creature, the aligner. And I think the message of this talk is that this is completely open. We have one example of some code that works this way, but this potentially can be very interesting in general in coding theory and constructing new codes that will work well in this setting. So that's the big message. If you don't get anything later, at least you know what this talk is about and from information theory perspective. By the way, if you have questions, you can stop me. I will not get to 90 minutes. I don't have to cover everything. It's enough for you to get something.
Hi, Yuval, this is Prakash. Can you hear me?
Information.
Hello?
It's working.
Hello? Can you hear me?
Okay.
Hi, can you hear
So
me?
a little introduction of myself. So what we do in my group, we take interesting applications. We take interesting applications from real information systems here on the right and try to construct new code that will help them work better. Here you see some pictures from papers of code that we constructed. And that is to say that today, what I talk about is one specific application, which is genomic data. You see it here. And I'm not an expert. It's not that I am an expert in genomics or anything like that. This is one example where we try to apply coding to an interesting application. Having said that, now I can pretend that I'm an expert in genomic data and will motivate this. So we have a lot of interesting applications for genomic data, not the least of which is COVID-19, the diagnosis of viruses. There are many more interesting applications for genomics, but all this is nothing compared to what we'll have soon when we'll get the advent of personal medicine. Basically, once genomics get into the everyday medical care of each of us, then we'll see an explosion of data of genomics, which we'll need to worry about and the solution. So that's the motivation. At that point, you may ask, what's special about genomic data? Information theory can deal with any data, and there are two answers to that. One is the nature of the information. Genomic data is a massively redundant information. 99.99% of the gene is identical between any two of us, which means all the interesting parts are hidden in this very fraction of non-redundant information, and that's an atypical scenario for information theory. And the second feature of genomic is the format of the data. The way the data is introduced to us from the source is not as a sequence as we are used to, here, the blue, but as reads. Those reads are snapshots from those sequences, from random positions that are unknown to us. Basically, what the source gives us is not the blue, but many of those reds in this picture, and that's also not a common scenario for information theory. By the way, I have to emphasize not to be confused with DNA storage, where those reads are part of the channel. Here, those reads are the input from the source to our coding. The source outputs those reads, and we need to communicate them or store them such that they can be reconstructed in different places or time. Okay, those are clear, the features. So because of their uniqueness, we have to think about genomic data separately from other data. So let's say a typical communication scenario, a real system where we'll need to deal with genomic data. So here you have a doctor's office, and here it has a small sequencing machine, a machine that generates those reads. And the problem is, as we said, most of this data is redundant, but the doctor doesn't have in his office the computational means to extract the wisdom from that massive data. So what he needs to do is to transmit all these reads to a centralized location, like in the cloud, and only there the processing exists in order to get the wisdom he needs. And that means that this doctor now has to send efficiently this data in a compressed form, because it needs to use the internet, which has limited bandwidth, to send those reads. And here I emphasize, not to confuse for the rest of the talk, all the communication that we assume in this talk is noise-free. We don't have the problem of errors in the channel. We'll soon have different types of errors, but the channel is noise-free, but still we need to compress those reads in order to fit into the limited bandwidth. And these are massive amounts of data. For one patient, we talk about 50 gigabytes, the typical size of genome sequence, including the multiplicities that we have to sequence with higher coverage. And that is very costly, cannot fit as is without doing some smart compression. Similar to that, we have a scenario in storage, where here we don't transmit the data to a different place, but we do have this time axis. So we sequence many patients at one time. And now we need to store all the outputs of the sequencer in some commodity storage box, because only later someone will ask us to process some specific individual, patient J, and only then we will know that we need to take it from the storage system and start processing. Most of the patients will never be processed, but still need to be stored efficiently in this commodity storage. And again, this is a noise-free, error-free storage box, not to be confused with DNA storage. So these are the practical settings. Now let's talk about the challenge of compressing reads and not sequences. So first, if you try to compress each read individually, it's not good. They are too short to get efficient compression individually. On the other hand, we get those reads out of context. We are not told where it is in the long sequence, so it's not clear how to use the fact that this read is taken from a long sequence. So respective to those two challenges, there are two state-of-the-art methods, existing methods for DNA compression. One is called reference-free. Basically, we take many of those reads and we group them together, hopefully the similar ones together, such that the similarities between them can be used in order to get compression. And the other method is called reference-based, where we take each read and at the encoder, slide it on some reference that is shared with the decoder, such that we can exploit the shared reference to encode only the differences from the reference and get efficient compression. And no matter what you choose, you pay a lot in terms of complexity. On the left, you have to group many reads and process them, the encoder. At the right, this sliding of the each read on the reference is very costly. And this is too complex for typical amount of resources that you get at the doctor's office. Yes. Oh yeah, I didn't talk about it yet. You're right that you kind of mentioned it in passing, but yeah, we will talk about the similarity. Of course, what we'll get here, the way we can compress is the similarity to the rest. Okay, so these are the two existing approaches. Let's put the reference-based method on the communication diagram that we had before. So now the encoder, we add to it a Y. Y is the reference sequence. It's this long sequence that is similar to those reads. We see that the input to the encoder is a batch of reads. Xi's are each a read, and we have a batch size M. We have many of those that we need to compress together. And now the encoder function is also depends on Y. And the way it works is now the Y is shared with the decoder, so it can use the information that it has to recover those Xi's using the reference. Okay, is that clear how reference-based work? Now what we propose in this work is a slight variation of the reference-based. We basically say, let's do decoder-only reference, get read, not assume any reference at the encoder. So you see now the encoding function is only a function of the reads themselves, but we still gain for compression from the reference by assuming that Y is available to the decoder. And the advantage here is clear. First, computation, so the doctor office doesn't have to, the computer of the doctor doesn't have to work hard on the reference. The complexity is low, and even storage cost is reduced. He doesn't have to store a Y. There are many of those such Ys. Doesn't need to store. And there's also a privacy advantage here. Suppose that these reads that are now being compressed are Jane's DNA, and in the cloud, Jane's sister is similar, it's a similar DNA, so this is Y. But still, Jane's sister doesn't want her data to reside at this local small town doctor for the sake of privacy. So she prefers, it's okay for her, for Y to be in the cloud, but not at the local doctor's office. So with removing Y from the encoder, we also get privacy. No, actually, Steppenwolf is, I'll get to it. Steppenwolf is also not decoder only, but let's get to it. Good comment, Sasha, because it moved me to the next slide. So if we want full sequence compression, the classical information theoretic sense, then this problem of decoder-only reference is solved, is part of a well-known scheme called the Slepian-Wolf coding. And even there are practical instantiations of the Slepian-Wolf scheme with the channel code that can help us do decoder recovery with decoder-only reference using the code. I'll explain how it works. So suppose we are told that X and Y, again, we are in the full sequence regime, not reads. X and Y are similar in the sense that they are a distance at most 1 from each other. You asked me about the similarity model. So here the similarity model is distance 1 at most. That means now that I can take a code, an error correcting code that is single error correcting, but use it a bit differently than usual. What I'll do, I'll partition it to the coset. I'll do the coset partition. And given X, what I'll transmit, the output of the encoder, will be the syndrome of the coset that this X belongs. Now I will send it to the other side, to the decoder, and notice that this operation did not use Y at all. It only used the assumption that Y is close to X. Exactly. Yeah, I'm sorry, I said the yeah, I'm sorry, I don't partition the code, I partition the space using the code. And now the decoder is similar to an error correcting decoder, but slightly different. So what it will do, it will have S, the syndrome from the encoder, and it will look for the closest vector to Y that has syndrome S. And if indeed the model of similarity applies, we are guaranteed to find X from S. Exactly. Exactly. Notice that it's slightly different than error correcting code. In error correcting code, we look for syndrome 0. We look for a code word closest to the received. Here we look for a word, not necessarily a code word, but in the coset with syndrome S. But algorithmically, we can use, if we have a syndrome decoder for error correcting code, we can use it slightly differently here, and we solve the problem. Okay. So
Yuval, can you hear me?
Full sequence
Hi.
decoder only compression.
Yuval, can you hear me? Hello.
Go to the closet leader. So
Hi, can you hear me?
and then what you are looking for is the code word, which is kind of above Y, the code, in the same column of the standard array. So recovering that code word and recovering Y is the same.
Yeah, it's equivalent, but operationally you cannot just, you need to do some transformation. You need to subtract from, to calculate the syndrome of Y, subtract from it S, and then
Yes.
put it in a standard.
Modulo, that is the same.
Yeah, as I said, this is we can think of a solved problem. But what we do in this work, we extend the coder only that information to the case of batches of reads. Remember, we have not a sequence, but those batches of reads. And what we do in our scheme, we first take those multiple reads.
Hello, can you hear me? Can you hear me? Hello? Hello?
Hi, Prakash.
Hi. I'm sorry. Can you hear me?
Yes.
I could not hear the discussion in the room. This comment has to do with Slepian Wolf. I was about to say that, but I wanted to add that since you're talking about security, once the source sequence X is compressed at the Slepian Wolf rate, then you can get security by just encrypting it with a symmetric key, because if the receiver also knows the key, then when you look at the conditional entropy of X plus the key, not X prime, the coded version plus the key, and the receiver knows the key, then there's no loss in compression rate. In other words, you can use the same idea with another layer of secret key encryption, just provide the key also to the receiver, and there is no loss in compression rate.
Okay, thanks, Prakash, for the comment, but I want to clarify that there is no security here.
No, I understand. I understand, because you said that you don't want to send X and Y together, encode them for various reasons. But all I'm saying is that you can get security for free in this scheme.
Okay. No, I mentioned privacy as motivation for why remove Y from the encoder.
Sure.
It's not part of the problem here to get some security.
No, I understand that. I'm just adding a comment. That's all. No point. Thank you.
Okay, thanks.
Yeah.
So this is the work of my student Yotam Gershon. So what we did first, we took the batch of reads and organized it as a one vector chi that we have here. And now we take this chi and put it into an encoder, basically a multiplication by an H matrix. The easiest thing you can imagine for encoder, unlike the more complex encoders that we had before. But now the question is, what is H? What is this matrix? And here we need a little more, actually much more than a full sequence case that we showed before. That's in addition to the usual code for reconstruction that we showed in the example. Now we need some more ingredients. We need some part of the code to do alignment, which I'll describe soon. And then part of the code to do something which is called validation. Again, I will explain later. Here, I just want to emphasize what the ingredients are of this scheme. And what we get is this sandwich, like a wedding cake H matrix. We have 3 layers that are readwise. So each HI here looks at one read and multiplies one portion read in the vector, and this bottom layer H4 encodes all the reads together to get some global resilience. I'll soon explain everything. So that's just the idea. So before I give more details on the code, I want to tell you about this known framework which we use that is called generalized concatenation. Generalized concatenation is a very powerful coding framework developed in Russia in the 70s. And basically the way it works, we have layers, multiple layers of the code. So we design multiple inner codes. Basically, we have a parity check matrices of inner codes that are nested. So we have the first code, S1, as a parity check matrix S1. Then we have a stronger code, S2, with more rows in the parity check, and so forth. And those codes are nested. So you see that the rows of the first rows of S2 appear in S1. So that's the structure that we have in the inner code. And now for each inner code, we match an outer code such that what we get as the code word needs to satisfy that the product of the inner matrix of the slice of that layer times the code word needs to be in the outer code for that slice, for that layer.
What's the
parity. The blue is the parity. Okay, so why generalized concatenation is so powerful? But there is one in Russian, I think 72. No? Maybe it's related. No, maybe the special case, it's called the tensor product code. Exactly. Yeah, exactly. Okay, so forget about Wolf, because we do use multiple layers. But why is it so powerful? Because we can kind of design this hierarchy in a way that we see that the inner codes become stronger as we go down in the layers. And at the same time, the outer codes become weaker. You see, we have less and less parity as we go down. And if we kind of balance it nicely, that as this one gets stronger, the other one gets weaker, we get the minimum distance or other properties to be the product of the two distances, the minimum taken over all layers. So long that we balance it correctly and the minimum is high, kind of min max, then we get a code with very strong properties. But that's kind of background. It's good to know in general, and it was useful for us. We use actually a generalized concatenation reconstruction. One step in between that and what we did is a prior work I did with Jacob Ziv of doing generalized concatenation codes, but for source code. Source coding for full sequences, not reads, full sequences. And here is a very similar idea, only that the part of the information is not transmitted. Here in the channel code, you send everything, this entire array, including the parity. But in the source coding version, you don't send the white, you only send the parity of the outer code. And what determines the compression rate is the ratio between the blue and the white. And clearly, if you reduce the blue, it's good because the compression rate decreases. Okay, so now after I told you the framework that we use, let me give you more details on those 4 layers that we have in our code. Okay, so layer 1, H1, is for alignment. Basically, we have to put in the code word some bits that will help the decoder do the alignment. Look for positions within Y that are relevant, that are useful to reconstruct the read that we now have. And again, I emphasize this alignment is not done by encoder. These are bits that the encoder puts for the decoder. It basically pushes the problem on the decoder. So that's the first bits that we have to put in the code word. Then maybe the most mundane bits is layer 2, the reconstruction. Exactly in the case of full sequences, a way to reconstruct X from a similar Y. Once we already found within the big Y an offset that is useful to reconstruct Y. But that's not enough because of this alignment that is imperfect. We'll soon see that sometimes we misalign, we false align. Then we need more bits to validate. Basically, validation is an operation that the decoder will do. It's a go, no go to decide if what we have in the outcome of the reconstruction is indeed a correct reconstruction or something that is incorrect. That's layer 3. And the final layer, as I said, this is the layer that crosses all the reads together. That's the outer code of the generalized concatenation scheme. Basically, any failure that we had in one of the earlier layers should be corrected by this outer code that we have here. Any questions about this? Okay, so now don't worry, I'll not go in deep into the algorithms. I just want to show you a picture that you kind of get the mechanics of how this works. So let's first look at the encoder. So here you see these nested inner codes, which we call H2. And the way the encoder works is first we take those L bits. Initially, these are the bits that we use for alignment. These bits are put in the code word, but then we don't think about them again in the encoding. They are left out of the encoder because they are sent as is to the decoder. And now the remaining n minus L bits, we just multiply by H2. This is the inner encoding. And the remaining degrees of the inner matrix are put into the outer encoder, such that what we get as the compression rate is the expression here. And here you see what we should do in order to reduce the compression rate. We see here both, we need to increase the dimension of the outer code or increase the dimension of the inner code. And we also see that those L bits that we pay for alignment, we pay for them here in the rate. So given the parameters of the code that we use, we know the compression rate from this equation. Now decoding is a bit more interesting. Decoding, first the decoder will do alignment. So it will use those L bits to look for good candidates to reconstruct X. But notice that it will find not one, but maybe more than one places within Y. Now each of those candidates will undergo reconstruction. That's the red. And after we did reconstruction, there is this validation step of checking how well we did, such that we'll not get false alignment and false reconstructions propagating to the outer code. And finally, after all those steps apply to the inner code, we send those outcomes to another step that is not shown here of outer decoding, of cleaning out all those places, all those reads for which we failed or we did some error. So that's how the decoding works. Now I want to give more better view on this alignment part of the scheme. So if this is Y here, and what we have is the read X, we can think of X as been taken from some offset of Y with some differences, those errors, those similarities. So we can think of X as undergoing some relatively good channel from Y. Again, this is not a real channel, a physical channel, but that's the model that we have for the data. But at the same time, when we align, what we use is a sample. We see those orange bits are a sample of the read. We cannot send the entire bit because then there's no read because there is no compression. So we send a sample. And because this is a small sample, we may get matches in terms of alignment that are improper, that are not real relevant position. And this we call improper alignment. And then we think that there is a very bad channel, maybe even a useless channel, between those improper alignment positions to X. And now the way we declare if a position is a alignment, we don't know if it's a proper or improper, that's not known to the decoder, but we have this Hamming criterion. If we know that the differences are only substitutions, then the criterion is to look at the sample of X versus the sample of Y. And if the Hamming distance between the two is at most T, and T is some parameter, then we declare it a match and we give it to reconstruction. If not, we declare it not and continue sliding the wing. And now you can see what I said in the first slide, that this alignment will affect the performance of the decoder. Because think of changing this T, maybe making it larger or smaller, can affect the success of the decoder to give us the correct read at the output. Okay, and now we also see why we have validation, exactly because of those improper alignment. Maybe they pass the alignment criterion, but we want those extra validation bits to reject them later before we pass them to the outer decoder. Okay, is that clear? Good, so now we get the picture and we can formulate the problem that we seek here. Basically, the goal is to compress a batch of reads that we know that Y is available at the decoder only. And now we define code with those parameters. So what we have here, M is the number of reads in the batch, N is the size of each read, R is the rate of the code that I showed you before how to calculate, and a new parameter here is a success probability. We are given a specification of what's the probability that we want to succeed in reconstructing the entire batch. And indeed, the code meets this qualification. If it succeeds, what we have here is just the probability of success of fully recovering everything. So in that sense, it's a lossless compression. We don't allow small changes, small errors, but we require it with probability at least be success. If this is satisfied, we say that the code has this qualification. Okay, now at that point, we have a part in the paper where I was supposed to tell you how I take all those parameters that we have. Notice that the parameters that we have, some of them are code parameters. The layer 1, layer 2, redundancy of the outer code, and also alignment parameters. How many bits we allocate for alignment, and also this threshold that we saw. How to take all those together with some source model to model the differences, and using some analysis that we do have in the paper, find the optimum, finding a code that has the minimum rate among all codes that gives success probability at least the specified value. Okay, that's an important part of the scheme. If we want to use it in practice, we need something like that, and we do have some results on that. But what I decided is to skip that, although it's interesting because I want to get to something more interesting, and that is dealing with deletions. So far, we only consider differences that are substitution, right? We talked about Hamming and all that. And we know that in reality, we also have other types of differences. And what we consider here is deletion. And in particular, the model that we consider is called the single deletion multiple substitution. What is this model? Let's first see an example. So if we have Y.
Hi, Yuval, may I ask a question or two questions, please?
Sure.
Yeah, so the first one is, in what you've done so far, the encoder does not use any knowledge of Y, correct? I missed some of the discussion. I missed all of the discussion that took place in the seminar room. So I might be repeating things or I might be speaking out of turn. But the question is, the encoder does not use Y at all, right?
Correct.
The encoder. Now, if you look at Slepian Wolf, we know that if the encoder knows the receiver sequence Y, there is no improvement in compression rate. Of course, this is all asymptotic. But in the actual encoding, there is simplification because the encoder can look at those X sequences that are jointly typical with the Y that it knows, the receiver side information, and work only with that set. Of course, this is a random coding argument, but still, the encoder can simplify its task through the knowledge of Y. Now, why can WHY can this not be reflected in an improved complexity scheme in the sense of what you're doing? So that's one question. The second question is, if you were to take all of this and build it into a probabilistic model, because you know that you said that 97, 98% of the bits in X and Y are similar. So if you model X as the input to a channel, a binary symmetric channel, where the probability of a bit flip is very low, so the probability that things get through without getting flipped is 0.99. And then you look at a standard linear code, and then the code word index that has to be sent, the code word, is simply the index of the syndrome, right? The coset index, that is the code word. If you were to use that scheme, then the receiver could simply do the standard linear code decoding. Why is that method not useful in this context? I know you're using the structure much more, but would such a what shall I call it, a very commonplace method not do well in this context?
Okay, let's start from the end of your question. What we have different here that is not covered by Slepian-Wolf is that the input here is not a sequence. It's a batch of reads. So we cannot assume there is a similar, if we organize, let's say we organize those reads as one linear vector, there's nothing similar to that in the decoder. The decoder needs to find.
I see. So there is no way of mapping this into a sequence.
Exactly. There's no easy way. We have this alignment in between.
Okay. All right. Yeah.
It comes to bite us.
I see. Okay, good. Thank you. I missed that part. So I thought you could map it into a sequence eventually. No.
Okay, and your earlier question, we can see here a model. Actually, this is, I skipped. You see a blank here.
Yeah.
It's something I skipped. I was supposed to tell you exactly what we assume for that analysis, for that optimization, but I skipped. There is a hint only here in this slide, those channels. So the source model is incorporated in those channels that we assume.
Okay.
The proper alignment. Think of it as a symmetric channel with some probability, and a useless channel from improper alignment. Because this part is unrelated to that part, then this is a useless channel, so we can rely on that when we analyze post-alignment probabilities and other measures.
Okay, very good. Thank you. Thank you.
Good questions, because it actually told me when I maybe missed some explanation.
Thank you.
So I decided to skip that part and talk about single deletion, multiple substitution. So first, let me tell you what it is. Why is this portion of the big capital Y sequence that is similar to X, what we called before the proper alignment? Then SDMS error means that we delete one bit, for example, this one, and we can have after that some substitution. In that case, 2. Two zeros then turned into 1. So we can say that X was obtained from Y after passing through a SDMS channel. And why is this a realistic model? Think of the first as deletion errors are more rare than substitution. That's why we only have one deletion compared to maybe many substitutions. But don't worry about the fact that it's only one. Think of the reads are pretty short. And if the reads are long enough that you see more than one with high probability, then you can shrink. The read does not have to adhere to some physical size. You can say, okay, now it's smaller, and get back to a SDMS model without worries. Okay, so that's the model that we treat now. Basically, now when we align, we no longer assume only substitutions, but also possibly one deletion. Yes. Yeah, but you do it not in operation, you do it in design time. Yes, so think that within the batch we'll have many deletions, but here we assume that in each read, at most one. And if you see, oh, this assumption is bad because I see more, first you have to think maybe there is some problem with your system, maybe because correcting too many deletions becomes hard, but no, it's not a disaster. You can just shrink the read and get back to that. No, you don't assume you know, but you have to consider the fact that it may happen. We'll soon, it will be clear. Yeah, it's a good point. Okay, more questions on the SDMS model? Okay, so now when we change the similarity model, we have to get back to the task list that we already done for substitutions and now apply them to that model. And we have two tasks. One is how to do alignment. Remember, before alignment was just Hamming. Now it should be something different. And that's not all. After that, we have to reconstruct the read from the similar place, from similar position with the possibly a deletion. So now we have to fill this task list with the new model. So let's talk about alignment metrics. So if we kind of insist on remaining with the Hamming metric, that's not good. How can we see that? Think of those two vectors. Think of one of them being y and the other being x. If you think of them as, if you compute the Hamming similarity, the Hamming distance between them, you get the maximal number. They are completely dissimilar, but it's clear that if you delete the first bit of this vector, you get something very similar to the other one. So intuitively, this should be closer than 4. So we need something else than the Hamming metric. The textbook solution to what we should do here is going to the Levenshtein distance, that is even much more general than that. The problem is complexity. To evaluate the Levenshtein distance, it's not linear. You need some dynamic programming, some complex. And remember that we have to do it for each shift of the read on Y, on the capital Y, and for each read. So you don't want to do Levenshtein distance in a massive scale. There's another solution from the computer engineering community. They call it shifted Hamming distance. That's actually a linear complexity measure, and it does capture these two as being similar, but it has the opposite power. It's too permitting, even it declares similar even to vectors that are not, and we'll show it formally. We'll analyze how bad this metric is in terms of false metric. Okay, so what we decided is we need something in between. We want a linear complexity, but something that will better reject false alignments. And we developed our own distance. So there are many formulas here. You don't have to kind of understand everything. I'll give you just the important parts. So we have this function that we can compute. Oh, by the way, we're given x of length n. That's the read. There's a detail here. We don't have the read, right? The read will only after reconstruction. But let's say for now, forget about this technicality. Let's say we have a full read of length n, and we have some candidate for alignment, small y of length n plus 1. And I was asked, how do I know if there was a deletion or not? I don't know. So I compare length n x to some length n plus 1. And maybe there is a deletion, maybe not. Okay, so given x and y, I can compute this function, phi j. That's basically, I just sum, it's a linear monotone function of t. I just sum the differences, but notice that x is unshifted and y is shifted, j positions. Now, similar to phi, I have the delta. So I subtract phi j plus 1 and phi j and get delta phi j. And now the formal definition of the new metric that we propose, which we call the shift compensating distance between x and y, is some function that we can easily compute minus something that we have to maximize. So it's still linear complexity, but we have this maximization. So we need to look for the t that maximizes this delta function. And once we found this max, we can substitute it here and get a number. Given x and y, we have a number that we declare the distance between x and y. Okay, is that clear, the formal definition of this distance? Okay, so now we can get some intuition. Where does it come from? So here you see the unshifted phi, and you see that before the deletion position, oh, by the way, in this example, there are no substitutions. In reality, we do have them, but here, for clarity, we only have one deletion. So before we get to the deletion position, phi 0 is constant 0 because it matches fully, x and y match fully. But after the deletion position, bad things start to happen. We go up in slope half. Because those sequences are unrelated when they are shifted, so half we are agreeing and half we disagree. And in the shifted version, phi 1, it's exactly the opposite. Before the deletion, random, slope half, and after we get this horizontal line. And what our metric tells us is that look for the place where the difference between the orange and the blue is maximal. So what we have here is just plotting this delta, and we found the peak. And indeed, we'll soon see that this peak is a good estimate of the deletion. But before that, all we need to calculate the metric is to find this t, and we have a number. Now I can tell you that this maximum is a good predictor of the deletion position, at least when we don't have substitutions, then it's a perfect estimate that t star plus 1 will give us exactly the position where there was the deletion. Okay, so this is the metric. Okay, so all the phis are the same. What changes is how much we shift y. X is not shifted, but as we progress, j equals 0 means we do XOR between xi and yi. And j equals 1, we do xi XOR yi plus 1. Single shift. Yeah, by the way, this metric can be generalized to higher more than one deletion, but then we no longer can guarantee that it's linear complexity. Then the maximization becomes more challenging. But here for one deletion, it's linear complexity because this maximization is trivial. What? No, there's no wraparound. There are just two sequences. We forget about capital Y. No, we don't need wraparound. No, we test all possibilities and find the maximum. N plus 1 exists because it's longer by 1. Yeah, we don't go beyond n+1. There's no need for a cyclic shift. Okay, so we invented the metric. Nice for us. The question is it good? So one thing I will not show you is the positive case. When x and y are actually close in the sense of SDMS, it actually gives us a small distance, zero distance, if there were no substitutions. But what may be more interesting is how it performs in the negative case. Think of, we actually talk about it in the paper, it's a semi-metric. Yeah, I'm not careful in my terminology. Yeah, I think we proved that it's a semi-metric. No, semi-metric because it's not the same length. So you need like a family of metrics. So you have n and n+1, you need to also consider the other, that x is n+1, and this does not really fit our application, so it's kind of an appendix in the paper. Yeah, we don't need the same. Yeah, we don't have symmetry because x is inherently fixed length, and y, yeah, y is can be any length depending on how many deletions we expect. Okay, so the more interesting part is how it performs when or false. So now we assume x and y same lengths as before, but they're unrelated. Think of IID sequences independent of each other, and we want to calculate the distribution of this new distance that we define. What's the probability that it will tell us 0, 1, 2, etc.? And it turns out we managed to calculate the exact distribution, and we'll tell you the high-level ideas. Again, we'll get into the details, and random walks, Sasha, your comment about random walks will be helpful here because that's what we use here. So now when we look at this delta phi 0 that we defined before, we can think about it as a series of delta i's, where each delta I is either 0 or plus minus 1. Where does it come from? Remember that delta phi subtracts phi 1 and phi 0. So if they are both the same, let's say both, each one adds either a 0, sorry, yeah, each one of the phi's adds either a 0 or a 1, right? Here, you either get a 0 or 1. So if both of them are the same, either 0 or 1, then delta I is 0. If phi 1 is 1, but phi 0 is 0, then the difference is 1, and we'll get plus 1, and the other way around. Okay, so that's how we get the 0 or plus minus 1. And also we know the probabilities of those events. 0 will get with probability half, and the others are probability quarter each. And that comes from the IID model. Okay, is that clear? That's the first step. And now we realize that this delta phi can be thought of as a random walk, symmetric random walk. Symmetric means that there is the same probability of going left or right, but maybe it's less common in textbook random walks. We also may get a null step. This 0 means that sometimes we will not move. We move left, right, or stay. But still, it's a clean model that we can analyze. Here is an example of two sequences and how they look as random walk. So we start always with a 0, and then we accumulate. The first step that happens is that only phi 1 is 1. That's why we get plus 1. Then both of them are the same, so it doesn't change. Then again, plus 1, and then a sequence of minus 1. And you see this is a description of those sequences as a random walk. And what's important for a metric is this max. Remember that in the definition of the distance, we have this maximization. So what will determine the distance that we get is what is this m. And what we need to do now is to find the distribution of those m's, and this will give us a distribution on the distance values. So it turned out to find the distribution of just m was not easy. So we added this argument of t. We now enumerate not just m, but also at what time, at what index this maximization was attained. This is t star. And it turns out that we can calculate the probability that a random walk like that attains a maximum of m at a point and t star. That's a combinatorial computation that we made. And that almost solved the problem because we still have, if we want, by the way, there is some monstrous combinatorial expression, you don't have to get into it. But in order to get this from the uniform distribution 4 to the n, it's not enough to count all probabilities of random walks. We need also to count for each random walk how many sequence pairs map into that. And there's a many to one there. One random walk can represent many pairs of sequences. So one missing part to get this expression is how many, to enumerate how many sequence pairs map into each random walk MT. And that luckily was also possible to calculate exactly, and we get this exact expression. That is maybe not very friendly, but can give us a closed form. And now we can plot the CDF of this distribution. That's in blue. What we see here is the value of our distance and the probability, the cumulative probability to get distance at most that number. And I remind you that here it's unrelated sequences. So what we prefer is to be on the high side. The higher we get the distance, the better the rejection will be of this false alignment. And what we see is indeed, we do much better than the previous metric proposed in this computer and engineering paper, where if you have unrelated sequences, the probability to give the distance at most 4 for them is more than half. With probability more than half, they will declare it pretty close. See, n is 18. Why would you say that an unrelated sequence is distance 4? And for us, the probability to have 4 or less is much smaller, is less than 0.1. So here you see the advantage of this metric in terms of rejection of false alignment. Question? So the metric is general. You can calculate it on anything. But maybe your question is about the source model. So in the source model, we assume that even a shift of 1 is unrelated, which may be wrong in practice, but if it's wrong, we can only benefit. Assuming that does not help us. Maybe it harms us, but so maybe if you know more about the sequence, you can improve further. But for the source model, we assume shifts are independent, but for the algorithms, everything works in any case. Okay, maybe a different picture of the same thing. What we plotted, again, the 3 metrics. And what we show here is we took a sequence and deleted, we took a Y and deleted 1 bit from it and got X. And now use this metric to find for different positions, what is the value of the metric. And what we see that the Hamming distance, as we guessed before, is not good, because even if we look at the correct deletion position, it gives us pretty high distance. and this distance is not much smaller than the background. So the Hamming distance will not allow us to differentiate between the correct deletion position to some random position. In the shifted Hamming, the prior linear time metric, we have the opposite problem. So indeed, in the correct position, it gives us 0. It declares similar, but now the problem is the other positions that are not much higher. Same as we saw in the previous plot, we see here that the background is very close to 0. And our metric gives exactly the best in between. We get a 0 for the correct deletion position and a background that is much higher than the previous. So we get green in both the true position and the random unrelated position. Okay, so that's about alignment with the SDMS metric. The last thing I have to do before I let you go home is to do the reconstruction. Okay, I found a good candidates for reconstruction, but now I have to do it. I have to reconstruct X with the deletion and substitution from this Y. And to do that, let's look at the channel coding equivalent of this problem. Same as we did for substitutions, that we've used the channel code. Let's first thing try to use a channel code. But notice that in channel coding, it's different. If here in a channel code you have some code word, the channel deletes and substitutes, and you need to recover back the original sequence. Our channel coding equivalent here will be slightly, our source coding equivalent will be slightly different. We have the source, Y. Sorry, we have the reference Y. The source generates something similar with a single deletion and multiple substitution. We did the encoding. And now the decoder, what it does, it uses the reference Y and the syndrome, same as we did for substitution, and it needs to decode. And the problem is when we see the problem this way, it's not easier than the problem here, the channel coding problem. And that's a problem because we know that it's not an easy problem. It's not a solved problem to have a code for a single deletion and multiple substitution. Maybe there is some progress, but it's not solved for general number of substitution. So it seems that we hit a dead end here in how we now reconstruct, but then we remember something that we added and we forgot about. Remember that we have this identifier, this sample of bits that we included just for the alignment. We didn't think about it as something that will help us for reconstruction, but here it will help us. Basically, what we'll get if we put the sample correctly in good positions, it will give us some hint, it will give the decoder some hint on where the deletion happened. Let's see how it works. So think of those orange positions as bits that we sampled. So we have them in the decoder. And now if we go back to the metric, and remember T star was then just used to calculate the distance. But now we think of T star as an estimate of the deletion position. And now there is an issue because here we don't have the entire read. We only have a sample. So T star is only an estimate on the orange position of the deletion. So we have this ambiguity. The deletion, let's say there is no substitution, the deletion can be anywhere from T star until the next orange, not including. The deletion can be anywhere here, but still it helps us narrow it down from the entire code word to the difference between the two sample bits. And now algorithmically, it gives us a much easier problem on reconstructing. We can basically try all of those positions within this ambiguity and decode X from Y. And what we have is an algorithm. What we'll do is we'll invoke a substitution-only decoder on each of those hypothesis. And now what we realize is that what we need to do, now each one of those will give us an outcome. Maybe some of them will fail, but some of them will give us some output code word, output hypothesis. What we have to do is to take the majority. We have many, and why majority? Because even if we miss by in a graceful way the exact position of the deletion, still a substitution only decoder has a graceful performance. So if we estimate it correctly and there are no substitution, we'll get all green. We'll get exactly the code word. But if we, let's say, missed by a bit, we only get one substitution because of that misestimation, and we may still get the same output word from the decoder. So as long as we are in the correct neighborhood of the exact deletion position, the majority, it will be expressed in the majority, and we'll be able to find it and reject all the others that are farther. Okay, and that's it. That we solved also the reconstruction problem. So now I can summarize the talk. What we propose here is some new coding scheme for efficient compression with decoder side information. An interesting part of this work is about the alignment. And as I said, the combination between the alignment and the code parameters. Now, getting back to the first slide, that's also where we need your help, coding theory people. Basically, this gives us many interesting open problems. What we have is one example of some code that works, but maybe there is much more to do here. First, what we assumed in our work is that we have some algebraic block code, which have pretty high decoding complexity, and we needed it for this assumption of guaranteed decoding. But maybe this will work better with LDPC codes or polar codes that are more probabilistic. So applying similar ideas to codes with reduced decoding complexity can be very helpful in practice. Another possibility, we only use one information from one alignment position to decode. We tried multiple ones, but at the end we used only one. We picked only one of those as the chosen one. Maybe we can use the information from all the similar segments of Y using some soft combining or other techniques to get a more reliable reconstruction. One very interesting topic is why use a sample for alignment. For convenience, we just sample the bits, and that gave us very easy Hamming or other metric alignment criterion. Maybe we should also use parity bits for that step. And basically, we use the parity bits will be used both for the alignment, and later they will help us also in reconstruction. Here, the alignment bits are not used later, except for the last trick I showed at the end. So maybe a better redundancy overall will be obtained if we make those alignment bits smarter. And another interesting topic, some of those alignments are false, which will give us that we try to reconstruct from a very far away word to what we have. And if we seek some indication of that, or codes that guarantee to detect those, we can help also further in rejection. And that reminds me of a known scheme in computer science that is called the locally testable codes. These are codes that allow you, from checking a few bits, to already determine that this is very far away from any code word. Don't continue trying with high probability, which can help us. We did not, our validation bits did not assume any such feature. We assumed some random drawing. We may be able to improve that. So if you are coding theorists, information theorists and you want to help, that's a partial list. If you want more, I can give you offline. So thank you very much. Did we get to 90 minutes?
Thank you. Thank you.
Yeah, so we used our construction is a generalized concatenation. So you see first the cartoon here. Yeah, and you see here, this is the hierarchy of the inner. Yeah, I think it can be same. Don't see a complication of going to quaternary, but you need codes of a higher alphabet. Yeah, there's no challenge here. Yeah, so we have a special. Our distance is specialized for SDMS, for single deletion. We have a generalization to R deletion, and this is better than Levenstein, because Levenstein gives you the edit distance, so it will count insertions, and so if you want this specialized model, you better define the matching metric, and also the complexity. Yeah, if you get to 2, now the maximization is, but we have a greedy. We can have a linear complexity by greedy maximization. You do it sequentially, and we empirically. No, cannot. So basically, here we needed to find T star to maximize. In the generalized case, we need to find 2 indices that maximize something, but now it's no longer linear because we need to check pairs. But what we saw empirically is that if we do it we'll first maximize for T1, and now given T1, we maximize T2. Sequence, we get very close to the actual optimum. So I think in practice, it will still be linear, but not theoretically. We didn't do that, yeah. Yeah, I think this distance is interesting in more generality than to our problem, because it captures, I didn't show it here, but it captures exactly what it means to be SDMS. It counts the number of the closest code word with a single deletion. Okay, thank you very much.
Thank you. Thank you very much. Thank you.
Thank you.
Bye.
Bye-bye.